Introducing a priori.
So let's walk through a live demonstration now. So what I'll do is we'll go through and we're going to evaluate an injection molded design. So I'll evaluate that in a priori, and we're going to assess alternative suppliers, consider different materials, and then compare design iterations as well. So when we're going to evaluate a design, we're going to look at manufacturability, cost, and sustainability in parallel. So let's switch over to a priori now. Now that we're in a priori, there's only the few main inputs for running an analysis, whether it's sustainability, cost, or manufacturability. So here we've pointed to the CAD file that we'd like to evaluate. We need to just answer those four basic questions you may be familiar with. What's your primary method of manufacturing? In this case, plastic molding. Where would you like to manufacture this? So we're going to look at this in China. What material and what annual volume? So at this point, a priori, we'll run through an analysis based off of those four primary inputs. So we'll take this, we'll process that through, and we'll come back with our analysis of cost, manufacturability, and sustainability. So if we come over here, we have our familiar bottoms-up analysis for cost. We have 22 cents of material, we have labor, we have overhead, giving us a $2.22 component in China currently. We also have the ability, to, as usual, to see manufacturing issues, whether it's draft angle issues, whether it's hole proximity, whether it's minimum wall thickness. All of this remains the same, whether we're running an analysis looking at cost or sustainability or manufacturability. But now what we have the ability to do is understand based off of our design, based off of our material, and based off of our region, what's the CO2 impact. So we can see the total CO2 for this design is 1.41 kilograms of CO2 equivalent. It's broken out by about 0.61 is coming from the material itself, and about zero point 0.8 is coming from that process. If we were to dive into that, we can actually see what's driving that. So what's the electricity factor of that region around the process? So we're going to understand the CO2 implications of that power grid in that region, as well as the energy consumption for producing that part. So this is based off of a bottoms-up analysis of cycle time for this part, understanding the cooling of the material, understanding how that geometry of the part drives it. So let's come and let's look at this. Let's move this over, for example, to a different supplier. So we know that we've been having supply chain issues from China. So let's move this over and see what would happen if we move this to Eastern Europe. So we want to maintain the part geometry, but let's just move this over to Eastern Europe, for example. So I'm just going to create a different scenario to analyze that. And then let's run our analysis with Eastern Europe. So we'll move it from China to Eastern Europe. We had a change in cost. We went from $2.22 to $2.57. Let's come over and look at the CO2 though. So we went from 1.4 kilograms of CO2 to 1.11. So we're moving the right direction here based off of this. It's sustainability wise, the cost did go up. But let's look at another version and see what would happen if we were to move this to Western Europe, for example. So let's create another scenario, this time for Western Europe, and let's see what this does for our overall sustainability. Same design, now in Western Europe, it went from $2.57 in Eastern to $3.77 in Western Europe. Let's see though, our CO2 went down once again. So now we're at 0.86 from that original starting point at 1.4 in China. So our CO2 has gone down, but our cost has gone up. And let's look at one final example. Let's look at this in the USA and see where we are cost-wise. And moving from Western Europe to USA, we had another cost increase. We went from $3.77 to $4.18. And then we can check our sustainability. We went from 1.01 in the US currently, and let's compare that back to Western Europe at 0.86. So not only did we have a cost increase by moving this to the US, but we also had an increase in carbon by producing this in the US based off of that regional energy grid. So let's look at what we just covered. So we looked at this injection molded part. We automatically optimize for process and feasibility. We identify those cost and quality drivers, and we provide suggestions, whether it's wall thickness or draft angle. We provide a detailed analysis of cost so you can understand whether it's material or labor or overhead that's driving that cost. And then finally, we provide that CO₂ equivalent for the material and manufacturing so you can understand what's driving it based off the region where you're manufacturing the part. Is it the electricity from that region? Is it the material itself? All of this will go into your overall analysis. So now let's go through and look at different materials and see what that does to manufacturing feasibility, cost, and sustainability. So now let's look at this design and let's change our materials. So let's come over to our sustainability guidance and let's look at our material. So here we can see in the US right now, about 60% of our overall CO₂ is coming from that material. About 40% is coming from the processing. So let's go through and let's actually look at some different materials. So we have it costed with ABS currently. Let's open it up and look at all materials. So now we have the ability to sort based off of the carbon of the material, the emissions factor, as well as the cost per volume. So we can actually go through and really understand what would give us a reduction in carbon. So sorting from that lowest carbon to the top, we have that ability to see, what's the emissions factor of those different materials. So here we're looking at our ABS, we're at 0.47 for carbon. We have the ability to sort and see what those different materials are. So let's find a similar material. For example, here we have a PBT material. It's going to be a similar density, a little bit higher. The cost per volume is going to be a little bit lower. Let's run it with this PBT material and see what that does to our overall carbon. So we were at 1.01 grams of kilograms of carbon. Let's rerun that and see what that does. So moving to that PBT material had a large reduction in the overall total carbon. So we went from 1.01 to 0.58, so almost cut the carbon in half. But let's come over and look at cost. And cost went the correct direction as well. So we went from $4.18 down to $1.80. We had a reduction in material, labor, and overhead based off of this new material. So we'll do that bottoms up analysis to understand the cycle time associated with processing that specific material. So we've just touched on manufacturability, cost, and sustainability, looking at different materials. So you can go through and cost a material individually, or you can tell a priori to go off and cost the part with all of my materials and come back with that lowest cost feasible material. All the while calculating sustainability. So you can understand the impacts of material change on manufacturability, cost, and sustainability. So let's take this design now and do some iterations on the design itself so we can compare those different design iterations and look at manufacturability, cost, and sustainability for different versions of this design, leveraging the feedback from a priori. So let's dive back into our design and let's focus on understanding the manufacturability, cost, and sustainability with looking at some design iterations. So let's dive into our design guidance and look at our potential manufacturing issues. So if we come over here, we can see our list of potential manufacturing issues. We have some draft angle issues, some hole proximity, but let's focus on this maximum wall thickness. So here with this current design, we've calculated a maximum wall thickness of 16.5 millimeters, and that's what's great. That's greater than the 3.1 that's recommended for this material. So let's dive in and see specifically where on that model that material issue is. So let's go through, let's go into our transparent mode, and we can actually highlight that specific area where there's a thickness violation. So right in the middle is our biggest thickness violation on that boss, as well as the ribs on the side have some thickness violations. So let's fast forward and look at a different design version of this. So let's go through and remove some of that thickness. So let's look and see what we can do for a different design here. So here I've got my revised design, taking that material, coring out some of the material in those thickest spots. So let's see where we are cost-wise. So right now we're at $1.70 for this design with $24,000 of tooling. Let's look and see where we are with our original. So we were at $1.80 with about almost $17,000 of tooling. So we've reduced the cost a little bit. Let's see what that does to our overall sustainability. So here we're at 0.58 kilograms of carbon. Let's look at this with our revised design. So 0.43. So we're moving the right direction. That material wall thickness has a large implication on the cooling time of the design. So the thicker the material, the longer it takes for that material to cool. So with our design, we have added some additional tooling to the part. It's resulted in 4 lifters for this cutout material. That's reflected in that tooling charge, the $24,000 instead of that $16,000. Let's fast forward one more time and look at this and see what would happen if we were to eliminate those side actions, go from 1 thick rib on each side to 2 thinner ribs, eliminating all that action. So let's see where we are cost-wise. So right now we're moving the correct direction cost-wise. We went from $1.80 to $1.70, now down to $1.46. We dropped our tooling charge closer to that original charge of $16,000. And let's see where we are sustainability. So that moved the right direction as well, 0.38 kilograms of carbon overall. So if we look back at that second design, it was 0.43. And then looking at that original 0.58. So we've moved the correct direction by minimizing that thickness of the part based off of the design guidance. So here we have the ability to optimize for manufacturability, cost, and sustainability in parallel. So based off of changing that design, we were able to reduce the cycle time. This led to a reduction in cost as well as a reduction in that CO₂. So reducing that material can have a very large impact on all 3 of these. And then in summary, we've evaluated an injection molded design. We've looked at potential quality issues, cost driving issues, as well as assessed alternative suppliers and alternative materials. And then we further refined our design by looking at design iterations to maximize the design based off of feedback from a priori.
A priori, making profitability and sustainability a reality for a better world.